Thank you, Mr. Chairman, for the kind introduction, and I would like to thank the organisers for the invitation to come and talk to you on this very critical issue of the effects, the potential health effects at doses of less than 100 millisieverts. This is a particular feature of this accident because actually I don't think that this has been particularly developed in any other earlier event. So this is a new feature to in radiological protection to try and impose some kind of a threshold. And we see it here in the proceedings of the Oversight Committee for the Fukushima Health Management Survey. It states that the latest effective radiation dose estimates show similar trends to those observed so far, since previous epidemiological studies indicate no significant health effects at doses of less than 100 millisievert. We concluded that radiation doses estimated so far are unlikely to cause adverse effects on health. So the question is this statement that since previous epidemiological studies indicate no significant health effects for doses less than 100 millisieverts, is this scientifically credible? They lean on a statement in a previous report by Untitled in 2008, and they cite this in support of what they've said. So far, neither the most informative LSS study, that's the lifespan study, and atomic bomb survivors, nor any other studies have provided conclusive evidence of carcinogenic effects from radiation at smaller than 100 millisievert doses. And so the issue here is what do they mean when they say conclusion? Because actually epidemiology, as somebody else has already said, cannot give you conclusive results. They can only give you a statistical probability. Probability that the increase or whatever you are observing is significant at some level. And typically, for epidemiological studies in radiological protection, we use what's called the 95% confidence level. That is that only 1 out of 20 times would we expect the result that we get to be a chance result. So we can look at this to understand how this concept works at tossing a coin to see whether the coin is biased to land on one side, and I've chosen heads up. And I've got a little experiment that we do. We toss the coin once, it lands heads up. We toss the coin twice, it lands up twice, heads up. When we have tossed it 10 times, we find that 7 cases out of the 10, it's landed heads up. And when we toss it 50 times, it's heads up 30 of those tosses. And when we do it 100 times, it's 61. Now let's look if there's any relationship between the number of tosses and the number of heads up, and in fact, it's a statistical thing, it's chance. And the question that we want to ask here is this coin that we've notionally tossed in this thought experiment, is this coin biased or not? When could we say that we shouldn't use it to get a random distribution, if you like, to call heads 1 and tails 0, and we want to get a row of randomly distributed noughts and ones, Could we use this coin for that, or would it be biased, producing more ones than noughts over a very long term? And so we can calculate what's called the p-value. Well, it's meaningless for one toss, but for two, the p-value here is 0.25. For 10 tosses, 7 heads, it's 0.117. For 50 tosses, with 30 heads, it's 0.042. Now it has crossed the 95% confidence boundary. This value here is less than 5%. And when we go on for the 100 tosses, it's quite clearly 99% certain that this coin is biased to land heads up. Now, when we're looking at the effects of radiation in a population, we're doing very much the same thing. We are looking to see if the general population that's been exposed to radiation is showing more disease than the population, similarly drawn population, the same number approximately of people, the same proportion of males and females, the age distribution similar. Then we are looking to see if we can see a difference between the exposed population and the non-exposed population. The non-exposed population we call the control group. So we're comparing the exposed group with the control group, and we're looking to see if we can see a difference in the two populations. So we're going to use the 95% confidence interval, because you can see that we have to increase the number of tosses of that coin quite dramatically in order to get improvements in the result. So we must assume that unscare means by conclusive means 95% confidence. And unscare admits quite freely that above 100 millisieverts, there's plenty of evidence at confidence intervals greater than 95% that there are studies which demonstrate risk. And we have many of them. The question is, do we have any below, with doses below 100 millisieverts? Because if we do, then unscare is wrong. Unscare has misrepresented the information. So there is one important point to note, and that is that the size of the population is very important. So if you have a group, let's say, of 1,000 people, and they're exposed to a relatively low dose of radiation, you will have considerable difficulty in seeing an effect at 95% confidence. If you had 10,000 people with the same dose, you have a much greater chance of seeing the effect. And it's possible, because statistics is a regular subject, you can calculate what the statistical power of a population will be, and you can say rather clearly whether you would expect to find an effect on the basis of current knowledge about the relationship between dose and effect. Of course, if your population is going to tell you something new, that, for example, they are more sensitive than you thought to radiation, then that calculation is somewhat inadequate. But I just want you to take on board that increasing the number of people in the population that you study makes it easier to detect a risk. And therefore, studies with a significance of over 95% at doses less than 100 millisieverts are at least as reliable as those above. So there is nothing magic about this 100 millisieverts. But we will come to see why it is used. So it has no special significance. It's false to assume that it does. And UNSCIA is actually misleading, deliberately misleading, in claiming that there might be a difference. And you notice that they don't. They use this word intrusive without really defining what they mean. We know they don't mean 100%. So this is what we call a weasel word. A word that is put in there in order to distract your attention. Somebody earlier today spoke about the power of language. Well, you're seeing it there. So let's see. We've already heard about from Dr. Rosen, about the study by Dr. Alice Stewart of pregnant women given X-rays back in the 1950s and 1960s. So it's a very old study. And there is, in fact, 8,500 cases of leukemia were compared with a similar number of controls. That is, women who didn't have X-ray diagnosis during their pregnancy. And the relative risk comes out in that study to be 1.47 for childhood leukemia in the children born from the women who received the X-rays. And that is significant at the 95% confidence interval. And that's just based on the number of films. Sometimes they took 2 films, sometimes just 1. But if you analyze it, again, in terms of the number of films, you can see that that figure, 1.47, is actually related to the number of films and therefore to the dose. So it is dose dependent. So we know with a high degree of confidence that it is the radiation that is causing this event. Now actually, the level of dose is less than 10 milligram at which the cancers are reduced. And that is more or less the lowest dose you can give to a single cell. Because either the cell gets an electron passing through it, and if it does, it's getting the dose of around 10 milligram, or it doesn't get an electron going through it, and then it doesn't get any dose at all. So actually, we can't really talk about the threshold less than 10 minutes, because it's just the physics does not allow you to have doses of 2 or 3 millisieverts. Now these results caused huge controversy at the time. Nobody wanted to believe that you could damage the health of a baby by irradiating its mother with something as considered to be very safe, a single X-ray. And the results have been extensively debated and reanalyzed, and the conclusion remains the same today as it was on the first analysis. And just as an aside, it's interesting to mention this study, this KIK study, it's called KIKK study in Germany, looking at the distribution of leukemia cases around nuclear power plants within 5 kilometers. And there is a significant increase in leukemia in children, which Ian Fairley believes is the result of irradiation of mothers, or pregnant women, due to releases of radioactivity into the air during the changing of fuels and the maintenance procedures. This is an ongoing issue. It will be investigated even further, but the point is that these doses cannot be very high. because there is no clear measurement of gradient of dose with distance to the power station. But it seems that these doses can be of only a few millisieverts. Now, it's not just children. Adults are also known to be sensitive to radiation at doses below 100 millisievert. And this study is also being referred to today. This is a study conducted by Dr. Cardis of more than 400,000 radiation workers. And the reason for the controversy when that paper was published in the BMJ was that this figure, 1.97, this risk ratio, was statistically significant at the 95% confidence level. And nobody wanted to believe that either, because the average cumulative dose for these workers was only 20 millisieverts. So this is in contrast to the Japanese bomb survivor study, where the doses ranged up to 2 gray, where in the region where we can measure the risk. And that central estimate was about 1.4, also significant at the 95% level. But the average doses are more like 100 millisievert. So the fact is those radiation workers, the average doses for the Japanese bomb survivors are higher than that. So this central estimate, 1.97, is of course higher than the 1.4, and it doesn't indicate conclusively, that is within the 95% confidence intervals, that low dose radiation is more damaging than high dose radiation, which we thought was the other way around. For many, many years, we assumed that at low dose rate, we could actually apply a factor 2 to, we could have twice as much at the low dose rate to get the same effect as at the high dose rate. Now it looks like it's the other way around. It's not going to be a factor 2, but it is possibly a bit more dangerous to be exposed at the low dose rate compared to the high. And of course, it's the Fukushima exposure is at the low dose rate, people living in contaminated areas. And finally, there's a growing body of evidence that ordinary diagnostic X-rays, and that includes CT scans, but not exclusively CT scans, is showing excess risks. So we are starting to be able to measure these risks at very low exposures as we build up larger and larger populations. And so the idea that there are lower risks per millisievert, per 100 millisieverts, at doses below 100 millisieverts is simply shown to be false by the evidence. We don't need the theory, we just need the evidence, and we have that evidence. And there is more. I'm not going to go through it in detail now. A paper is in preparation, and we are hoping to get it accepted, but it's being turned down by at least one journal. But what I want to point out is that this is not new. Possibly you can't read this list of authors here, but these are the great and the good of radiobiology in approximately 2003, 2002. And they pointed out that if you look at the data on the atomic bomb survivors, and you see it here, the doses in millisieverts up to 400 millisieverts, coming down to close to 0. And this dotted line is the extrapolated line linearly from 2 gray, so 2,000 millisieverts. And we look down at this end, and we see that the majority of the spot points where you can make those kind of estimates lie above that line, which suggests that the risk at low dose could be higher than the average risk determined. That figure we saw of 1.4, the average risk determined from the whole atomic bomb survivor population. So this was current in 2003. It was published in PNAS, Proceedings of the National Academy of Sciences, very reputable journal, and therefore I think it's not in any way new to accept that these risks exist at doses of less than 100 milliseconds. Now, the important benchmark here is 20 millisieverts per year, as that is the level at which people might well be expected to live. External exposure of 20 millisieverts per year. So I want to just look what this means in terms of risks. And the first thing that we need to consider is the dose rate in subsequent years after the accident. So when the accident took place, if you found an area that was 20 millisieverts per year immediately after the accident, will have dropped by a factor 10 a year on. And that's due to the decay of the fresh, short-lived radioisotopes. If you go now to 3 or 4 years after the accident, and you take a place which is 20 millisieverts per year, their drop over that period of I think it was actually, 10 years. The drop over 10 years will not be anything like that. It will be down by a factor of about 2. But we'll assume a factor 2. It will vary from place to place, or rather more from time to time. And we'll use the data from the DEAR Committee of 2007, DEAR 7, that was also mentioned today. And I think this is the most solid data on this that we have. And you can see here the age against the number of cases per 100,000 exposed people. And you can see how the risk increases for young people dramatically, and for females much faster than for males. And I'm going to take a worst case scenario, if you like, by taking the example of a female. This figure, DDRF, unscare, I mean, I think many people have thought that the DDRF of 1 rather than 2, which I mentioned earlier, should be used. And unscare actually in the latest report was used 1. I recommend the use of 1. Perhaps one of the good points that they've made. So in this worst case scenario, I'm going to look at a girl, 1 year of age, and then introduced into an environment giving 20 millisieverts per year, and dropping to 10 millisieverts per year after 10 years. An average dose rate of 15 millisieverts per year. And so she's going to get, over that period, 150 millisieverts, and her lifetime cancer risk for that 150 millisieverts will turn out to be 6.75% by using that graph that I showed you on the previous slide. And in addition, there could be a further risk of non-cancer disease, which is much more difficult to quantify, but it could well be of a similar magnitude. So within the first 11 years of her life, she could have incurred a risk of serious disease within her lifetime of some 10 to 15%. Very rough figures. So we won't be concerned with decimal places. Now if we compare that with the lifetime risk to a male radiation worker, working from age 20 to 60 years and receiving the maximum allowable dose under the ICRP limits of 5 millisievert per year, giving him a lifetime dose of 200 millisievert. And this is a quite feasible scenario for a radiation worker to achieve over the next few decades. So, from the previous graph, we see that his risk accrued over those 40 years is roughly 2% for 200 millisieverts. And we could double that to allow for non-cancer disease. That's just a rough estimate. So 4% of serious disease for a lifetime of radiation work. Now, we could also look at the case of a girl, a 1-year-old girl, living for 10 years in a non-contaminated region and just receiving natural background radiation, plus 1 millisievert per year of public dose. Oh, sorry, I'm told the time is over. I'll be very quick. So if we look at her risk, it's 2 to 3%, and that would imply more or less everywhere in the world. So we saw that the effects were observable down to 10 millisievert, and so that's a reasonable estimate of risk. Now, what would be the effect of assuming this 100 millisievert threshold? So we would see that the girl living in the contaminated area would get a 2 to 3% risk if you neglected everything below 100 millisievert. The radiation worker would end up with 2% total risk, and the girl living in the non-contaminated area, 0 risk. So, I will end now. I'm just pointing out that I've only taken in I'll leave that point. So the conclusion is that it is not sustainable scientifically to assume that the risk will be lower at below 100 millisievert. And almost certainly the risk is linearly dependent on dose down to 0, in other words, LMT. But now, 3.5 years after the accident, we don't have a detailed picture of the risks that are involved to the population from this accident. Thank you.